hello again. This is Kinematics 2. I decided to play with some of my video settings, so as you can see in the bottom corner, you can see me. So you can be rest assured that I am doing these problems. But anyway, let's work on the problem that we have up here, which is a rocket sled. Let me read it. This is Kinematics 2. So we have a rocket sled. Let me get my pen going. Here we go. Perfect. Okay, we have a rocket sled that accelerates for 50 meters per second squared for 5 seconds, coasts for 3 seconds. I underline these numbers. Coast is a key word. And then deploys a braking parachute and decelerates, coming to a halt. The questions are, what is the maximum velocity of the sled and what distance did it travel? So let me break up this problem. First of all, this thing is doing 3 different things, as you can see, separated by the commas and the and. So first it accelerates. So I'm going to call this 1. I'm going to break this down into the parts. And that's where it's going to be speeding up, more or less. I assume that this is where the maximum velocity is going to occur because it's going from rest and then it gains speed. The word coast means that it basically keeps its speed. So during the coasting section, it's going to have a different motion. So I'm going to call this section 2. Then it starts to brake. So this is another type of motion, section 3. So we have a rocket sled. Here's our rocket sled. Here it goes. During section 1, it's going to accelerate. So we know that, or we can assume that it doesn't have any initial velocity since it doesn't specify specifically. And then it's going to have, I'm going to say this is where the maximum velocity happens, right here. During this point, we are accelerating, and it will be positive since we're gaining speed. And during this time, it's going to take 5 seconds. So this is all section 1. Then the rocket car is going to coast for 3 seconds. I'm not drawing this to scale, by the way. I am just kind of more or less just picking some random distances here. Coasting, again, no acceleration. So we're going to have 0 acceleration. Not necessary to write this, but I'm just going to be really specific here. And I have a time here of 3 seconds. And then section 3, we slow down, right? So that means if we come to a halt, I underline that keyword, the final velocity of this area, or this section 3, is 0. The velocity here is going to be the same as here, the max velocity, because it hasn't, this is the constant velocity part, so constant V. Right here. And then we're going to have a deceleration. Since we're slowing down, this becomes a negative number like this. So there you have it. So when I like to do these problems or solve problems, I definitely draw them out because I think, first of all, if you understand it, you're going to draw it visually, and that's where you can kind of see if you can piece things together. And again, just to see it makes things and problem solving a lot easier. So let's solve problem, or part A. Part A is, what is Vmax? So in order to solve this part, I'm going to actually use section 1 because that's where we have all of our information. In section 1, we have the initial velocity is 0. Acceleration is 50 meters per second squared. We want basically the final velocity, and we have time. 5 seconds. So luckily, we have all the ingredients to solve or use this kinematic equation right here. Check that out. I'm going to go ahead and plug in. Initial velocity being 0, acceleration being 50, and then we have our time as 5 seconds. So as you might imagine, although what we get here is 50 times 5, 250 meters per second. And notice that one of the seconds gets canceled by the seconds right here because this is on top of the fraction. Anyway, this is the answer to part A. It's pretty fast, and I guess that makes sense because it is a rocket car, so it's going to go really fast. So that's section 1. Okay. Next question, part B. It says, what is the total distance traveled? So more or less, I need to know D1, D2, and D3. So I'm just going to go ahead and label that. D1, D2, D3. Just like that. So because I want the total distance traveled, as you might imagine, I'm going to find the distance for each section, just like that, and then add them all together. So, sorry about the camera, I guess it keeps adjusting. Pretty weird. So let's do that. So this first section, this is solve for D1. Here's all my information, and technically I could add to my information box or list. We have this. So pretty much any kinematic equation will be useful with the distance. So personally, I like this equation for this problem specifically is delta x equals VIT plus 1/2 AT squared. Again, you can use any kinematic equation to solve this, but I like this because first of all, the initial velocity is 0, so this whole term goes away. Second of all, it's already solved for displacement, or more or less DI, or the distance. So delta x, I'm using different symbols. This is the same as this, more or less, distance, is going to equal to 1/2 the acceleration times time, which we have both of. The acceleration is 50 here, and the time is our 5 seconds, and that will be squared. So I will solve this on my calculator. Got my calculator right here. 0.5 or 1/2 times 50 times 5 squared gives me 625 meters, like that. Okay, 625. That's part 1. So this is D1. Alright, so more or less I'm just going to do the same kind of process for each section. I'm going to scroll my paper down a little bit. Here we go. And just leave that up here. So like I said, during section 2, so let's do that, we said it's constant velocity because the keyword was coasting. Coasting means you're not gaining or losing any speed, you're keeping it more or less, so that's constant. That makes solving this section pretty simple because we can use the constant velocity equation as such. Or I might, sometimes, I apologize, I just use D for short. Sorry, I paused it for a quick second, so there might be a jump in what we just talked about. Okay, so this is our constant velocity equation. I use the proper term, which is x instead of the d, but regardless, this is a distance measurement. We want to find and solve for d. So if I do some quick algebra, you will see that if I rearrange this to v times t, I get the expression for our distance. So during that section, let's just bring it up a little bit. There we go. What we have is we have the velocity here. Now, since it's coasting, the velocity during this section is going to remain the same as the velocity here. So what we get is our velocity is 250. It doesn't need to find our initial because it's just going to be the same. And then we're going to multiply by the time during that section in which it's coasting, so that's the 3 seconds here. So, although I'm doing mental math, I just want to make sure. 250 times 3, great. The math works, 750 meters. So that is D2, if you will. Like that. Okay, now let's finish off with the third section. So the third section is decelerating. So let me go over here. This is the deceleration, or slowing down. So what do we have for that? So we are going to slow down from the 250, so we do have initial velocity. Notice that it doesn't tell you this. This is something you have to assume, and you have to, assume logically, of course. We do have the acceleration, which is the -3 meters per second. Notice once again that I added the negative to represent the deceleration or the slowdown. And I think that is it in terms of information. The only other thing that we could use is, because it's coming to a halt, we can actually assume that it's 0. So there's our pieces of information, and we need to know the distance. So I'm going to use, the distance symbol, which is delta x. So even though it looks like we don't have a lot of information in the problem, in terms of numbers, we actually do. And we're using a lot of assumptions from the problem. So that's something that you'll have to get comfortable with, is making logical assumptions to replace the missing numbers with numbers you can use. Taking a look at this, I hope you'll realize that this will be the appropriate kinematic equation to use to solve for this. Because notice that we have the final initial velocity and the acceleration, and we're looking for that piece right there. Okay, so what I'm going to do is plug in those values. So 0. This whole thing is squared, not just the units, okay? This is going to be 250. Plus 2. It's very important that you put that negative sign. Otherwise, you're going to get the signs mixed up and say you're going backwards instead of forward, because we're slowing down while moving forward, not backwards. And this is just our symbol delta x. Now remember, this is the same as me solving for this. These are interchanged. Alright, that's a delta, sorry, but that's delta x. There we have it. So I'm going to solve for this. I'm actually going to do the additional step. So this will be 0, of course, but I'm going to move this over, which becomes negative. So first I'm going to square the 250, and I get a large number. And then I got to subtract this out to get to this section. So what I get here, doing the math very quickly, I hope you're okay with that, is negative 625,000 equals 2 times 3 is negative 6 delta x. The point of me doing this is show you that these negatives basically go away, so that you're left with a positive displacement, which again makes sense because you're moving forward. You don't need to show these steps. Usually I'm okay if you just skip it, step it and go to solving it. So basically, to get this by itself, I need to divide by 6 on both sides. I get delta x equals 10,416 meters, 0.67. There we go. So that is D3. So naturally, what I'm going to do is add the 3 together. Let's do that in a fun color. So D1 is 625. This is 750. This was 10,416.67 meters. Notice if you calculate this as you do this, I just round to a couple decimal places, which is sufficient. So the total distance would be the addition of the 3. And I will do that plus 750 plus 625. The answer is 11,791.67, around 7 meters, just like that. Ta-da! And that is part B. Alright, I hope you enjoyed that video, and if you have any questions, just let me know. Have a nice day.